Nothing crazy.
Right? Yeah, I know, right? Yeah, that's how I feel after doing
Yeah.
projects with like native trees. I've done it like 3 times for different classes, so now I'm just like I've got like that's that. Like, yeah, they finally got it. Yeah. Yeah. Yeah, after my biology class last spring, it's like some of my it's just like for me as a that's a big loss. Like yeah, just being able to tell Oregon parents just went hard versus yeah. Bark is hard. And the leaves it's
You're either like first versus top.
oh no. Yeah, it's crazy how I'm learning to have stuff like that. Like I'm doing so many so many different things. I'm sure it does. I was really right, right. Normally they give you the nitro. Yeah, I had a friend like that. She's allergic to like a bunch of different fruits, like almost all fruits, and like no-go on top of like dogs and cats and just so much. Yeah, by all means,
South is you're going north, you're going west.
I feel so lucky.
You're going west, which is
That's pretty cool. Yeah. And also a lot of people die because of lactose. Just like don't care. They just eat dairy. Yeah. That's it. Yeah, they always say it's like useless. But it actually does have some purpose. Yeah. I mean, it makes sense to get rid of them. Yeah. Yeah, it's like my doctor or my dentist for like years when I was little. Weird stuff. Like I just lab yesterday. Or witness yesterday. Right. Wow, you're just so powerful. Everything is connected. Oh yeah. I mean, that's essential for survival.
All right, let's go ahead and get started. So just a couple of housekeeping is I realize I need to move at least a few people off the wait list and at least into an official class. And so we're still trying to play Jenga with you all and figure out where exactly we're going to place however many floaters we have. And so if you came to Tuesday Lab and you went there and you got a seat, you're secure. So if you didn't go to Tuesday Lab, even if you sign up for Tuesday, you should show up to Thursday today so you can check in with me and talk, and so we can figure out if you're going to be in Tuesday next week or what we're doing with you. And then so I originally had foresight, and I knew that, okay, maybe we need to find a spot for a few extras, but then biology has also grown, so they kind of took over my contingency plans. So my next backup plan is if anybody could physically make it to these times, either to switch labs permanently, so maybe looking for, like, again, this is why I have to see who shows up today, but I'm thinking maybe a group of 4 students. Ideally, if y'all could coordinate and if you could meet, again, either Monday or Wednesday, 9 a.m. to 12 p.m., that's when I have my Chem 104 lab in the exact same spot we do it. So it'd be a little chaotic, but I could do it, right? Get my Chem 104 students going, and then there'd be plenty of space for, 4 or 5 or however many that is. So if anybody wanted to make that change in their schedule, again, you don't have to do anything, right, officially with RCC. This is just with us. And then the other thing is if you do miss a week, and I know I have at least one student who had to miss the first week due to medical issues, and so we don't have a lot of flexibility, but this would be a good spot to have a little bit of flexibility. If you do miss lab, you could make up a lab at this time as well. So I'm putting it out there, but again, we can figure out all the details once you actually show up physically to lab. So make sure you get these codes written down if you're on the wait list. Just stick yourself in some section. So I believe everybody's okay with the lecture recitation. I have both 49 in all those, but I just need to get people off the lab wait list, and we need to figure out a physical spot for you. Otherwise, worst case, we might be sticking y'all in the stock room or something. Like I said, we're still playing Jenga and see who physically shows up. All right, so I will see the other half of you that I didn't see on Tuesday today. And all right, so how Thursdays are gonna go, because again, you have that weird scheduling. So I'll lecture for about an hour, so we'll finish chapter 1. We probably won't make it through all of chapter 2, but then I'll stop myself at noon. And then normally, like I said, we would have a longer quiz, but today is just a welcome assignment, so it'll probably only take you 10 minutes. And then the rest of the time is yours in recitation, so I can go around, answer questions, do whatever. If you want to leave, you can leave, but you're more than welcome to sit, do your work, and then again, we'll meet for lab at 1:30. A couple of other things I want to put on your radar just before we begin. So if you have looked at lab or were in lab, you know you have to do some reading in the Journal of Chemical Education. So I wanted to go over how to get there. And so if you go to RCC's website, go to the library page, and then you can click this guides button, and then go for chemistry, and then right here it links to the journal, and then of course, right, you can search in here. So once you get to this page, you should be able to find it. Again, if you still can't find it, just let me know. And then if you're on campus, so notice it says, right, access provided by RCC, but if you're off campus, it should just prompt you to log in and then you put in your student credentials. But again, if you have issues with off-campus access, just let me know. And then if you're ever, especially, so I won't introduce our paper assignment yet. I'll save that for maybe week 2 or 3, get you guys at least settled. But eventually you'll have to do some research. And so if you ever come across papers that you can't access, just send me an email and I can try to get it for you as well, because I know there's a lot of things behind paywalls. I'm more than happy to help. So other things that should be on your radar is it's never too early to start thinking about doing undergrad research. And so you might want to check out, and I can post a link to this later. So this is the NSF website, and then you go down for this RU experiences. So this is research for undergrads. And so I would just encourage you to start poking around and see like what campuses have research going on, what programs are they offering, and then, you know, start applying. And I'm more than happy to write letters of recommendation. I had one student last year, I believe, who like did some program. And so, you know, obviously you can pick your own discipline. I'm not going to go through this, but right, everything's on there. You could search for whatever your particular interest is, but whatever your area is, right, you want to start progressing in that field or what you think you're interested in, right? Because you might start doing that field and you're like, wait, I don't actually want to do this, or maybe I want to pivot in a different direction. So you always want to get that hands-on experience. I would encourage that as well. And you can always chat with me, again, after class, during lab. Always email me individually as well. So more than happy to help you navigate. And so don't forget, if you want to join my personal outreach / maybe research activities, just let me know as well. So again, sign up for outreach, which I'm going to also say is kind of Earth Club, but I'm kind of rebranding Earth Club to be less so like earthy and more sciencey, if that makes sense to people. So yeah, if you also want to be involved in Earth Club, maybe be an officer, that also looks good for your resume. So we might need more people.
Can I talk about engineering club too?
Oh yeah, if you want to plug engineering, go for it.
So, hi, my name is Vaughn, and currently I am the sole member of RCC's engineering club. So I'm wanting to do Invent Oregon this year, and if you're interested in doing a collaborative project with me, let me know. I'm on campus. I work on the 3rd floor in CS, so I'm around a lot. So yeah, just come up to me and say hi.
And then if you don't want to talk to Vaughn, you can also bug Dusty too, right? Dusty's still doing engineering club, correct?
Yes, yeah.
Yeah, and we should work on collaborations. If that tickles your interest too, I'm trying to get people interested in collaborating. So like engineering, you know, bring people back on campus, do activities. Again, get y'all teaching, because that's really what it's about, is getting you teaching the next generation as well. All right, I think that's all the housekeeping stuff. Are there any housekeeping questions that we needed to go over before we dive in? All right, so let's dive in. See how far we get. And so the last little bit of your chapter is just talking about our different units of energy. And I think when we were talking about laws, maybe we mentioned this equation, so 1/2 mv squared. So let's see if we can derive then our units of energy. And so do people know what mass is generally given in physics with this equation? Try the standard unit for physics. So yeah, chemistry, our base unit is grams, but in physics, they plug in a different unit for mass. Yeah, that would also work, but well, that's the gravitational. So kind of, so 9.81. So this was our gravitational potential energy. But when you solve for kinetic energy in physics, what do they put for mass? Kilograms. I don't know who said that. Kilograms. So yes, mass is in kilograms, and then what's velocity given in? Yeah, meters per second, so that's meters over second squared, and so, right, kilograms, meters squared over seconds squared. And so this is what a joule is. So now I'll rewrite that. So a joule is this unit, so kilogram, meter squared over second squared. So when you plug in this formula, again in kilograms, the energy given is in joules. And so yesterday I mentioned I couldn't remember this formula, so here it is. So this is, of course, the formula for potential energy. So we mentioned our gravitational acceleration and then height. So this should also give us units, so kilograms, height, and then acceleration, meter per second squared. So again, gives us our same joule unit back out. So you can see that's consistent at least. And so now just other kind of these scales of energy. And of course, number one on here, energy from the sun that hits the earth in one day is 1.5 times 10 to the 23rd joules. I don't know why I said kilojoules. 10 to the 23rd joules. And of course, this is, right, the argument for solar energy is, wow, look at all this energy. But of course, that's also distributed throughout the entire earth. So that's very diffuse. And later we can argue about whether solar energy is worth it or not. And so largest nuclear device ever tested, 2.5 times 10 to the 17th joules. Approximate energy of the atomic bomb on Hiroshima, so 8.4 times 10 to the 13th. Pretty large. And then we can go down to the small, so energy of an electron in a hydrogen atom, so 2 times 10 to the negative 18 joules. Or if people remember, somebody brought up that attajoules. So yes, that's where it has the relevance when we're talking about individual electrons. We're on the attajoules scale. And then energy of a photon is about 10 to the negative 19. So we'll do some calculations. And it's really fascinating. I think your light or your eye can detect only 2 or 3 photons. It's pretty incredible. And so we also have this diagram, and so this is usually in reference to, of course, right, some sort of object falling, so our gravitational potential, so of course at its highest point right here, or it looks like somebody threw this one, so if you were to throw it, which of course, let's see, I can't throw, so right, that would give you that sort of diagram that's shown here. And of course, when that marker was flying at the apex, it was reaching, right, its highest potential energy and then fell back down. And so all that is to say that our energy total then is, of course, equal to our total potential energy plus our total kinetic energy. And then, of course, in chemistry, we'll often look at the potential energy in bonds, so we'll quantify that, again, later on down the line. And then, of course, kinetic energy, at least in chemistry, is related to temperature. So again, we'll explore those relationships throughout the 200 series. So other just jargon and definitions we should know is, of course, right, looking at our data. So we have to be able to also assess our data, right? You're doing an experiment, and then, well, is my experiment good? Is there some sort of maybe inherent flaw in my setup? And then how can we kind of assess that? And so precision refers to the closeness of measured values to one another. So is your experiment, right, set up in at least a systematic way? So are they clustered, or is everything too random, too crazy, where you can't actually distinguish any pattern? And then accuracy, and of course this only works if you're trying to compare it to something. So maybe you're trying to recalculate the speed of light, and so then, right, you'd want to compare your number. So is is it coming out how I expected? You know, did I set up everything correctly? So of course you'd want to double check your setup. And so now looking at this, we can kind of look at what might give us these errors. So what can you say about A? What do you notice? What might it indicate? Let's see. Let's go for the back.
Potential wind, external force.
So maybe, so talking about just a target, so some sort of, I'll just say like systematic flaw. So not necessarily even a target board, just like if your data's clustered but not what you expect, what does that show you? So I like the wind idea, right? So the wind, if you are physically putting it towards a target, maybe there's something, right, a constant force. And so what should you do with your setup then? Yeah.
Should maybe recalibrate your machinery or your tools because something you're doing, it is keeping your data clustered, but it is not the thing that you predicted would happen.
Exactly. So everybody hear that, right? So that's an indication. So maybe there's some sort of systemic flaw. Again, you want to reevaluate that. Are your calculations correct? Is everything standardized or what it should have been? And so what do we say about B? Any comments? Let's go on the, are you Grace? So user error. And you know, honestly, this data isn't like too bad, especially once you get into like the real world of science, right? Nothing is perfect. But yeah, maybe some sort of user error, especially, you know, if you were to move on to like analytical chemistry, you'll find like, oh, I'm kind of in the right area, but maybe I need to redo that, you know, kind of be more precise, really take my time, measure really carefully with the balance, right? And so again, you might want to reassess your experiment. And of course, right, we're talking very vaguely. So once you get into your specific disciplines, then you start talking about very specifically, like what kind of data are we looking for? Like what should that look like? How do we verify the data? And that's something else that, you know, you have to be very cognizant about as a scientist and just a human, is just like your own, you know, bias, your confirmation bias. And that's the most dangerous thing, right? You as a chemist, you want to make what you want to make, but you have to be careful, like, does your data really tell you that? And there's been instances where, like, people thought they put one metal in their compound, everything looked great, but then, like, the mass spec was off, and it turned out they actually had, like, vanadium instead of, or no, it was manganese instead of iron in their compound, because the iron they used, their, like, iron chloride source was contaminated, and then for some reason, that manganese compound was just more favorable. So that was the one they were actually characterizing. So yeah, it's very, very tricky, but you know, always good to, again, you know, reassess, am I really seeing what I'm seeing? You know, can I repeat it? Can I prove it in different ways? How many different ways can I prove it? And so what about C? What can we say about C? It's perfect. So it's perfect. So, like the terminology, so accurate, precise. And again, right, this usually doesn't happen in the cherry world. So this is probably, again, if you're trying to recalculate some sort of constant, then you might be looking for this sort of thing. But again, usually your data is not this clean. Then what do we say about D?
Maybe your hypothesis was wrong. Nothing is where it should be. Inconsistent.
Yeah, that's a good word, inconsistent. Yeah, and that's, I like the whole reevaluate your hypothesis or experiment. You know, maybe we can't measure it. Maybe this data isn't even marking what we're trying to show. And so then in lab, you calculated your percent error. And so your percent error is just defined as your average value minus your true value over your true value. Again, whatever that true value may be. And it depends. You'll see, right, they they came up with some standard of the popcorn water percentage is 13.5. Again, right, it'd be nice, like, how do we re-verify that? But we'll just accept that as our true value. And then usually we kind of take the absolute value, or you can report it either way, so it doesn't really matter, right? If it's a negative or positive, you just care more about the difference with the percent error. So let's formally go over how to do our math operations too with our sig figs. And again, I think people were getting a hang of it in lab, but we'll just kind of go over it. And so multiplication and division, I always say this is kind of the easiest to do. And so it's just the least precise measured value determines the number of sig figs. So we'll look at an example. But right, you just do your multiplication, division, and then see, well, how many sig figs did I have? And then you round appropriately to those sig figs. And then addition and subtraction. So to me, this could be a little trickier, just because, at least for me, I like seeing it elementary school style with the decimals, so you can see how many decimals I need to report to. And with that, again, you're just looking, the smallest decimal measurement determines your sig fig. And we'll do some examples right now so it's clear. And so this also kind of shows you why you want to write as many digits as you can in lab so that you don't have this awkward scenario. And let me just fire up my calculator so we're all on the same page. And so let's say we did this in lab. We're trying to find some area. So 3.56 times 4. And so, right, we get this nice number of 14.24. But then how many sig figs am I limited to? Well, how many does the 4 have, though? Yeah, 1. Oops. And so, right, again, that's why in lab, give yourselves as many decimals as you can, because now, well, we probably should have written it, right, as 4.00 centimeters, so we could have had those 3 sig figs. But since we only gave 1, well, now we have to round this, and so now it rounds down to 10. That's really, it feels really awkward, right? But that's why it's so important in lab to give yourself every decimal and every value that your glassware reports. So now let's look at this one. So we'll punch it in, 2.050 times 5. So how many sig figs should our answer have? I see a bunch of 2s. And so now we have that little awkward scenario. Well, I need to report 10, but I need 2 sig figs, not 1. So 2 sig figs. And so that's where you can write it like that, which is kind of awkward, or the better, like they wrote it there, right, 1.0, so that we know, well, I bothered to report this after the decimal point, so that is significant. And then times 10 to the 1. And so again, same thing with this example, give yourself enough sig figs. So now we only have 1 sig fig again. I'll punch it in just for clarity, but so there we get 5, and so we can only report to 1 sig fig, just like our limitation here. And so now looking at this one, don't let the conversion factors confuse you, because remember, they don't count. So this is just a conversion factor, this is a conversion factor, right? All these are just conversion factors. So then we want to report to the 2 sig figs then of what we started converting with. And so they did the math, the calculator spat out this answer, and then you round again just how you normally would, so rounding up to 1.4 meters. Everybody feel okay with that? All right, feel free to slow me down. That was already a comment in my 104 classes. I tend to get really excited and talk fast, and we have a lot of material, especially the 200 level, but yeah, feel free to slow me down. I know I get overexcited. All right, so addition, subtraction, this is where, I like seeing it this way. Obviously, you can do it however you want, but basically, if this is our limiting factor, so this is only 2 after, so then we need to round appropriately, and let's just follow along. So 23.467 plus our 313.21. And so it spits out this answer, but again, we can only report to 2 after, so of course, rounding up with that 7, and that gives you the 336.68 inches there. Yeah. So it's just whichever one has the least, right? So this one was the one that dictated it for this example, so it only went to 2 after, so that's why, okay, we need to cut it off here, but then you want to round, right? You don't want to just truncate it, you want to just round appropriately. Well, right, it's limited still, because there's going to be some physical limitation in lab usually. Like unless you're doing some ridiculously precise calculation, in which case you would, keep going. So if everything is that precise where you're adding 2 values that go, 7 after the decimal point, that's your answer, right? 7 after the decimal point. But usually there's some sort of limitation. Yeah, and because at some point, right, you reach just a physical limitation of just how accurately you can even like obtain that value. And so in this case, again, this is a good example of why you want to give yourself as many digits as you can, because now we end up with this, what I call an awkward scenario. Yeah.
So would you fix that by adding 2 zeros to the 457?
The 457? Yeah, except, right, we don't know what this value came from, so that's why I say, like, in lab, you have to get it right? Because now once we take the data over here, now I don't know, maybe your ruler was not that precise, and maybe this was as accurate as you could get it, right? So I can't make that assumption anymore. So yeah, exactly, that's why in lab, right, you want to give yourself everything. So, right, best practice, lab, yes, you should have recorded 457.00, right, again, assuming your ruler was that accurate, which they generally are. And so that would help you. But, let's just say, right, someone gave us this data, or maybe they were using really shitty equipment, and this was, as accurate as they could record it. Then we end up with this scenario. So we'll punch it in. So minus 68. So, right, we get that answer, except, well, we can report to none after the decimal point because of this value. Again, right, this is our limiting value. So 0 decimals after, right, the period. So then we just have to round to 456.
So if that 457 had like a decimal point and then a 00, you would then have 2 significant figures after the decimal point.
Yeah, so let's just write that. So 0.68. So if we had done that, then we could have reported 456.32, right? That would work. If they had only given us, right, 457.0 centimeters minus our 0.68, right? Now we would report to 456.3. So good reminder to give yourself every digit, so then when you're doing your calculations later at home, you don't start getting awkward answers. But then when I'm looking at your work and like checking it, I just look at like how many sig figs you reported, right? So if you only wrote down 4, that's what I'm running with your calculations. Yeah, so it's be consistent just with yourself as well. So, don't try to like fix it or, know, okay, I got to get myself 2 after the decimal point with my leg. All right, that sums up chapter 2. So any questions, or chapter 1, any questions before we go to 2? Last lingering thoughts? I see people in the corner. All right, so 2, we start our atoms and molecules. And so we start with our definition of matter. So matter is just composed of particles. Really, we'll call them atoms and molecules. And then these subatomic particles, such as protons, neutrons, electrons, make up our atoms. So we'll go into our atomic structure later on as we progress through the course. And then we'll find that molecules are composed of atoms, and we want to just add under there 2 or more different atoms. And we'll look at, again, what I really mean by that. And of course, all chemistry is how do things react? How can we force things to do new cool stuff? How can we make new bonds? And how these particles interact, their intermolecular forces, all that will give it the physical properties. And you'll start to see that again as we progress through the course. Why are things solids? Why are other things liquids, right? All that is all those intermolecular forces, how they interact, their bonding, their structure, everything. It's really beautiful. And so matter is defined as anything that has mass and occupies space, again, including your air, so don't forget about that. And of course, chemistry seeks to understand matter, and again, reactions. And chemists always want to do new reactions, make new bonds. So that's what makes me tick personally, is bonding and new bonding motifs. You can't really get funding, though, for bonding, but we'll talk about that later. And so atoms are just our basic submicroscopic particles that constitute the fundamental building blocks. And so, right, if it's on your periodic table, though, it's an atom. So you can, unfortunately, we don't have a periodic table in here, but that's why I give you your own to cherish and love, right? So anytime you have a question, is it an atom? First step, right, look at the periodic table. Is it on there? And if it's not, well then, right, is it a molecule? Is it a mixture? And so you'll want to be able to determine that. And so we'll look at molecules. And so those are obviously, again, 2 or more atoms in a specific geometric arrangement. And again, that geometric arrangement dictates all its behavior. And so an element, oh, sorry. And so again, an element is just a substance that cannot be broken down. And, right, we use the terms kind of element and atoms pretty interchangeably, right? An element is just referring to an atom. But then we'll look into what it means by some things are in their elemental forms. And so it's always a single type of atom, whereas a compound is 2 or more elements, and then this is a key word here, fixed definite proportions, right? So that's different from like alloys, which those are kind of more like percentages and more kind of an art form in some ways, where a compound, right, is really defined. Anybody give me a compound? It's a good compound. More. Carbon dioxide. It's a good one. H2O. And there we're seeing, right, defined proportions, 1:2 ratio for here, 2:1 there. Any others you want to? Ammonia. Methane. I'm feeling a lot of gases today. Yeah, table salt. NaCl. Excellent. Propane. And so again, right here's our periodic table. And so of course we'll be interested, how do things react and combine? Especially, right, table salt is always one of my favorite examples. You take sodium, which is super reactive chlorine, right, a toxic gas, they come together and make table salt. So let's look at a few oddities. So what are diatomic molecules? Do people know who are the diatomics? Yeah.
Diatomic molecules are things that like to be paired together in nature. So things like hydrogen likes to be paired together. Things like oxygen likes to be paired together with another oxygen molecule. What's another one?
Let's see, you said hydrogen, oxygen.
I think fluorine is one of them.
How many are there? Do people?
There's always 2.
Oh, do you know how many diatomics are?
Oh,
So
I
there
want
are
to say there's 6 diatomic. No, there's 7.
7. So let's highlight them and then we'll write them. So we had hydrogen. So hydrogen's kind of the lone one you don't want to forget about. But then the rest make that little pattern that looks like a 7. So you can hopefully remember there's 7. So 1, 2, 3, 4, 5, 6, 7. There's our 7, but of course, right, there's only 6 in our 7. And so you're correct. So fluorine, so don't forget chlorine, bromine, and iodine are also diatomics, and of course, oxygen and nitrogen. And so as we progress throughout the course, I think it won't really be until second quarter where we really dive into it and understand kind of the true bonding. How are these diatomics? How are they bonding with each other? Why are they? So all those are questions we're going to answer and be dancing around, at least for a while. Let's see, so nitrogen. One, two, three, 4, 5, 6, 7, okay. And then what are allotropes? Do people know? Or maybe even an example of an allotrope? Any ideas? Many of you have an allotrope in your hand. So lead, so what's lead truly? Yeah, so carbon has lots of allotropes, so we named one, so graphite. What are other allotropes of carbon?
Graphene.
So graphene. What else?
Charcoal.
So I don't know if isn't charcoal more like amorphous carbon?
Yeah.
Oops, I can't even spell charcoal. No, they can be anything. But that would be a molecule then, because that's 2 different.
So would an allotrope be any atom that can be arranged in different patterns?
Yes. And so let's.
Charcoal isn't, but coal is an allotrope.
Coal is officially. Okay, I'll put coal. We're still missing the shiny one of carbon that people like.
I heard someone say diamond.
Oh, I missed it. You guys got to help me out. Diamond. So yeah, so I always say, right, Wikipedia is nice for science, but not good for history or current events. But I like looking at the pretty pictures on here. And so, like you were coming to the conclusion, it's just different 3D geometrical arrangements of the same atom. And so now we can start answering the question of why you can write with some forms of carbon and then wear a nice shiny ring of another. And so this is graphite, and so notice, right, it has really strong bonds as the sheets, but then it has these weaker intermolecular forces here, and so that's why it shaves off and nice little sheets that you can write in, versus diamond. So diamond, the carbons are arranged in this tetrahedral pattern, and so that gives it its strength. But interestingly enough, this is the thermodynamically favorable product. So this would not occur on your life scale, but if you watched a diamond for long enough, it would turn back to graphite. So. And so I think people mentioned other structures. So let's see, is graphene on there? So they didn't have glassy carbon. Oh, they did put amorphous carbon. So I would be like charcoal. But you can see graphite. The other famous one, so this is a good one to know, this D here, the buckyball C60. So this was some famous research done, can't remember when now, maybe the 90s or 80s at Rice University where they first made this. So this was the first kind of carbon nanotube-ish structure. So it started with the buckyball, but then it later evolved to this carbon nanotube, and now they're making all sorts of different materials and doing research with that down there. And so again, other structures, you can see there are other structures out there. All right, other elements with allotropes. So people probably know some of phosphorus. So I'll show phosphorus. And so again, phosphorus has the same thing. And so sometimes, right, you can see this as P4, and some people have heard of P4. And so white phosphorus is often known as P4. So of course this is used in military applications. And again, you can appreciate at least, right, the geometrical arrangement. And so obviously this one is very pyrophoric. I think some people are aware of it. And then there's red phosphorus. So this is, again, a different geometric rearrangement. Apparently can be formed from heating white phosphorus. And then other phosphorus, so you can have this violet phosphorus structure and black phosphorus. So again, right, they're all phosphorus, so it's still an element. It's just different geometrical rearrangements.
Would selenium be another example of an allotrope?
I would personally have to look it up.
I'm guessing just based on the table. I'm drawing a line.
I'm trying. So apparently, let's see, I think it did say it had allotropes. So yeah, Wikipedia mentions that selenium has a few allotropes. So I'm just naming kind of the more common ones. And so yeah, you could totally, there are probably many more allotropes that exist. The main one, or not the main one, but the other one that I wanted to point out is sulfur. Because sometimes you see sulfur in a reaction, people will write S8. But yeah, this is certainly not an exhaustive list, so you kind of understand anytime you see just one type of element in different geometrical rearrangements, that could be an allotrope. And so sulfur, let's just show what it looks like. So this is the solid state structure of sulfur. So again, it makes this funky 8-membered ring there. That's kind of interesting. So different geometrical arrangements. All right, so again, key point, it's the same atom. And so anytime you get two or more different ones, that's a molecule. So let's see. I'm trying to think. Maybe we'll stop here because I want to do our demo. And so let's start kind of thinking about the difference between, right, atoms and molecules and a chemical reaction here. And so I have a couple of diatomics. So I have hydrogen, of course. I have oxygen, and you can tell oxygen is kind of dense, it's not floating. And then our mixture there of hydrogen and oxygen. And so, right, we want to light them up. And of course, right, we like fire and chemistry explosions. But we're going to see kind of the difference in the combustion, right? Because we're going to see with the hydrogen and oxygen, we're just burning the elements itself. And then we should get a slightly larger boom for the two of them. since that will actually be, right, a chemical reaction will be forming water as well as burning everything. So I just need one brave volunteer.
Volunteer.
All right, let's have one person do one. Who's trying to call me right now?
You can do it.
Yeah. Well, we can switch off, so let me just get set up here.
Having a home lab is fun.
All right, so you want to help me out for the first one?
I sure can.
So I will have you hold. So let's start off with hydrogen. And let's kind of position you. So stand kind of over here. So I'm trying to, and then, yeah, so you'll kind
Hold it
of
out
point
this
it.
way.
Yeah. So I'm trying not to light the screen on fire.
Alright.
Yeah. Or you on fire. So definitely hold it out your max length. And so what was hydrogen? What's the famous hydrogen explosion? Hindenburg. So what was Hindenburg? So yeah, it was a blimp, and that they used hydrogen. And so let's get ready for this.
You can see the heat.
All right.
Hotter than I expected.
Do you want to do the next one?
Yeah, do we want to do oxygen next? Or
Yeah, so we'll do oxygen. So you can tell oxygen, right, is less, or excuse me, more dense than our air. So, right, hydrogen, obviously they thought it was a good idea for the blimp since it's nice and light. So now we have oxygen. And let's see, hopefully we don't scare anyone. Oops. Yeah, hold it out.
That's just a birthday candle.
Yeah.
Yeah, it's. So hold it out nice and far away from you. Yeah. So we all like hydrogen. All right, who's ready? Who wants to do the combo?
I can do the combo if no one else.
Oh, let's get someone. We'll get some new victim.
Yeah, but I hope they know chemistry in session.
Yeah.
I'm sure they do.
Yes. So I don't know. Hopefully we don't. Hopefully we won't. If not, chemistry is here. So yeah, hold it out nice and far away from you. So there you can see, right, the explosive difference from the reaction. So again, kind of giving you a sense of the difference. And thank you all, you brave volunteers, for doing that. All right, now that we scared some people. So I think that's probably a good place to end up on, because I like to give you guys a 10-minute break before we do our official recitation exam thing. And so I know some people mentioned they have to go, so if you really got to go, I have the quiz, so please do this so I can again see who's attending. And if you're for some reason online, which shouldn't be the case, but let me know, and then we'll reconvene, do our quiz. You'll free to go unless you have lab. So again, if you didn't come to Tuesday lab, please check in with me today. All right, excellent. And thank you all again, those 3 brave volunteers.